So the second topic I want to present you is about physics-informed architectures. In other words, deep learning meets dynamical systems. This is in particular interesting. So let's take a look at very deep. So the story goes like this. Let's take a look at the very deep architecture that you may already know. Okay, you haven't been implementing it because it's hard. Because yeah, there are like there can be hundreds of layers. It's called ResNet, residual network. So there are many layers. Okay. And each of them, you train weights for each layer. So in a nutshell, how this works, and there's also skip connections, okay, not visible on this picture. So there's always some skip connections. So you are carrying the result from you are carrying the input to the output. Okay, so the computation is, imagine that your image is like X, XK is image propagated, input propagated through the kth layer. So the algorithm goes like this. So you just compute many times the operation. You iterate this operation where you take the previous iterate and you add, okay, some value which is computed using trainable weights in the given layer. So there are like K is like a layer index kind of, and you multiply it times something small, not to avoid you know exploding gradients, for example. Yeah. So ResNet is that was a big breakthrough because that was like kind of first architecture which was very deep. It had like over 100 layers, and there were like 2, 3. It was made possible mainly due to these 2 tricks. The first one, which is skip connection. So basically, that's why I have XK here. So I take I kind of propagate the input through the layer, and so that kind of avoids the issue with vanishing gradients that you may know. And then I add something small times the trainable layer evaluated on the input, and this thing here avoids the exploding gradient. So if you look at this, this looks like well-known Euler time-stepping scheme. So this is like really old, you know, Euler, 19th century, whatever. Yeah, people already computed things like that, but there were motivation was like dynamical systems, right? So you want to kind of integrate a celestial mechanics system, for example, yeah? A planetary system in time. So you do things like that. So the only thing is that each layer is like independent. So in ResNet, I kind of change the weights each step, right? So I cannot, it doesn't approach fixed point or anything because the weights are different. So imagine that I want to make each block to compute the same operation now. I want to train it. Okay, so I say I don't have independent layers that each of them having their own parameters, but I use only one set of parameters for each layer in ResNet, and then the equation will change into that one. I don't have Fk anymore. I have just F, and this is exactly the solution, Euler solution for differential equation. Yeah, differential equation is like continuous. Okay, so the difference between this one, so this is like a solution that you can compute, actually, because you just iterate, yeah, this is solution for some continuous equation, which is known as differential equation, yeah, and this can produce really nice, like you can see the most classic Lorentz attractor. So basically, the point moves on this butterfly kind of in a chaotic way, and so this equations they can have really complicated solutions, right? So and we want to kind of embed this into ResNet or any differential equation, and actually. There's the original paper, which is really which started like the whole. It started the whole new research area. It's called Neural Ordinary Differential Equations. And this paper won best paper. This is like best paper award from NeurIPS, like 2019 or something. So it's only 2 years old, but already motivated a lot of research. So if you look at the citations, it's really a lot of people working on that nowadays. Okay, so yeah, so the idea in this paper is to interpret kind of neural networks as dynamical systems, you know, and to train dynamical systems instead. And the major application was related with this should be a movie with ResNets. Okay, so the first major application is that you can think of the deep ResNet layers as dynamical system. So instead of training each layer separately, let's train a vector field, yeah. So and then you can see, okay, so the comparison here, so residual versus ODE network. So residual will be like discrete, yeah. So first of all, if you have like time series data, for example, your data points need to be distributed uniformly for this to work. But if you have ODE network, it's like continuous, right? Because okay, we don't train like time stepping scheme. We train a vector field of a continuous differential equation. So then the network becomes continuous, and you can actually work with non-uniform data. Okay, the samples can be distributed non-uniformly. It will still work. That's one big advantage. Another one is that memory efficiency. Okay, because I told you, instead of using each layer, the weights in each layer separately, you have just one set of weights, which is defining the vector field. And apparently, this will have the same accuracy as the original ResNet. And the memory efficiency is huge. Instead of storing weights for each layer, which there can be hundreds of layers, and each layer is like thousands, okay, millions even of weights, you just have one you just keep one layer, one set of weights. And this, if you do this, it will have the same accuracy. And then another application, unfortunately, this video doesn't. Okay, another application, actually, this can be used also for computing data distributions. Okay, using so-called normalizing flows approach. So there are many more applications. Even you can approximate data distributions using that. Yeah. Which makes it so interesting. Okay, so now, okay, we can. What do we want to learn? Okay, if I just said that I want to put dynamical system inside of neural network, but what type of dynamical system I want to learn? Okay, now, because if I train weights, I'm training weights to solve some image classification task. And now I told you that I do some continuous business, okay? I have some vector field, etc. So the interpretation is that this is taken from another paper about neural ODEs. So you can see a flow. So what do you expect is that when you run this flow on your data in the latent space, kind of, it will separate different classes. Okay, so you have like mixed data set, right, in the latent space, and then you run it through the dynamical system that you trained, and you kind of, one class goes here, another class goes another place in the latent space, you know, and you can see separation. That's like ideal, because then once you have this, it's easy to classify. Like if you separate in latent space of the classes, and that's what these dynamical systems in this application are doing. Okay, you can see some examples from improved implementations, right? Blue and red, it's clearly separates. Yeah, you can see the trajectories of your data points in the latent space here. Yeah, and they get separated. So yeah, there are many questions to be looked at in this domain. So because we have some relation with, you know, differential equations, the natural question is what type of solver to use and how to adjust time step. What is the best vector field here? Yeah. What are the properties of once you learn it? We should look at properties to understand better, okay? Because maybe there are some improvements to be done. So what are the type of properties we can look are attractors, okay? So like the trajectories are kind of converging towards some compact structure. Fixed points, okay? So you converge to a single point always, or periodic orbits, okay? So maybe we should kind of look for solutions that are periodic in time. And actually, there's a recent paper where they actually showed that you should look for more periodic solutions in this context, because like you don't want to feature space to be contracted into some fixed point.